Welcome, everybody. We're going to be working on Module 2 tonight, and we're going to begin with talking about an important feature of Python, and that is functions. And functions are one of these things in Python that we've been kind of already using right from the beginning. So when we first did a print statement, that's a function. And we just were looking at like floating point and input functions and others. But basically, what a function is a named block of code. And once you take a series of statements and name them, I can just call that whole series of statements by its name and then execute it. To do this in Python, we use a keyword to define our function. And this is a little weird, right? But this is how Python does it. We use def, or in other words, defining the function. Notice that we give it a name. It's followed by parentheses and a colon. Once you get that definition in place, there is a required minimum indent on the next line of at least 2 spaces. Depending on your IDE, it'll be 2 spaces, 3, 4, or 5 when you do this. If you do not indent it, the function does not operate. I am going to demonstrate this stuff, but let's just take an example here, and I'll take it into their little try it editor so you can see how it works. So I'm defining the block of code, right? There's the indent, and I have a print statement. And let's just, change it so you know that it's actually working. But I want you to notice if I remove this, right? So if I just define a function and run it, for taking a long time, but basically the result's going to be nothing. It's not going to do anything. Why? I defined the function. I didn't ask it to run. This is the weird part of it. If you think about, like when you use the print statement, you call the name of the function, print, and then you put something inside the parentheses. But unless I call my function, it's not going to execute its steps. So now I'm going to run it, and it will put hello there on the screen. Interestingly, if I wanted to say something more than hello there, right? Let's say I want to say hello there, goodbye. Notice how this statement's also indented. Now it will execute both of those statements because both of those are part of that defined function, right? So the beauty of this is if you have a complex series of steps that you perform to complete an action every time, you can put them into a function and then have them execute with one single command. And then if I take that command and run it, let's run it again, right? And in fact, I'll run it a whole bunch of times and hit run. It saves me the effort of taking all the individual commands inside that function and reiterating them in code. So I don't have to like repeat these statements. So I'm only putting 2 statements in here, but it could be 100 or 1,000 statements. And I can make them all trigger with one function call. So you define it, you give it a name with parentheses, you put a colon at the end, and when you put the colon in there, anything that's part of that function has to be indented. The indentation has to be consistent. So if you're using 2 spaces, everything's got to be 2 spaces. If it's 4 spaces, everything's got to be 4 spaces. So for example, if I take this print statement and push it back there and now run the function, watch what it does. It first executes this, then it executes my function call. Because of no indentation, it's not part of the function anymore. Right? So this is weird because in a traditional language, right, like Java, let's just use that as an example. You define what's inside of a function by putting curly brackets around it, right? Opening and closing curly brackets. Python defines blocks of code that are together only through the indentation. That's a little weird. right? And it takes a little getting used to. But that's an example of how it works. So we will create blocks of code, and then we will call it multiple times to perform actions. This next example is kind of an interesting one because you notice that the parentheses have something inside them. So in other words, we're sending a value to it. And so the parentheses are a mechanism for sending information into a function. We technically call this either an argument or a parameter. By the way, you hear programmers use both words. There is actually a correct way to refer to it. When I call a function and send in a value, that's an argument. When I receive it inside the function, it's a parameter, right? So this is very goofy kind of talk, but that's one of those things, by the way, and I say this every time I teach those two words, is programmers kind of interchangeably use those words, an argument, a parameter, and they kind of mean the same thing. There is a formally correct way to do it. The formally correct way is the receiving location, which is the function, it's a parameter. The sending location, it's an argument, right? And I don't want to argue about it. I just want to tell you. But so there's a Monty Python joke in there somewhere, I think, right? All right. So that's actually enough for right now to have us do what we need to do. When we do run a function, though, and we do pass arguments into it, in this case, we're sending in a string and we're outputting two strings joined together, but we can also send in numbers, right? And another thing we haven't talked about yet, but you can send in multiple values at the same time. So if you send in multiple values, you just basically put a comma in between the stuff that you're sending in. So I could have like F name, L name, last name, etc. And I could just separate them with commas. Yeah, we often call those args, by the way. So you can think pirates if you wish. So here's what we're going to build here. We're going to build an area calculator. And so basically the requirements are this. Create a get area function. Notice how it's named. That does the following. It accepts two parameters. So it's going to receive two items. Returns the area by multiplying the two parameters. Then we're going to create a calculate area from user function that does the following, accepts no parameters, gets two floating point numbers from the user, calculates the area using the previous function. So this function will call that function, and then prints the results rounded to the hundredths place. Run the calculate area from user function 3 times. All right, so this is what they're going to do. Input a number, input a second number, they'll give us the area. Do it again, input a number, input a second number, give us the area, and repeat. So we're going to do that 3 times over. And the notes here are, make sure to use the correct functions to convert your inputs. Okay, so like whether we're using floating point or integers, we have to consider that, right? Because remember, whenever they type it in at the prompt, it's text. And I want you to notice all the numbers going in and all the numbers going out. Well, most of the numbers going in are decimals, except for one. So that one's going to attempt to break it, but we're going to work around that. All right, I'm going to go ahead and get my little notes here on the screen. And we're going to start building. So I'm going to start with a little bit of file management. So I'm going to go into my file system here, and I have a folder where I'm putting my work for this semester for this class. I am going to create a new folder. I'm going to call it Module 2 Labs. So all of my labs will go into that folder. In Visual Studio Code, I'm going to come up here to the top and open a folder. I should be close, right? I am very close to it. And I'm going to go into Module 2 Labs, select that folder, and now that will be the one that opens up here in the sidebar. I'm going to get rid of the welcome screen here because I just don't need it, but this folder is the active one. So I'm going to create a new file, and I'm just going to call this mod 2 lab1, dot pi is what I'm going to call it. You want to call it area calculator, that's fine. That's what it's going to be. All right. A couple of notes I'm going to kind of drop in here and kind of use this sort of as a lecturing tool, right? Instead of using a PowerPoint, so be thankful, right? It's not a PowerPoint. But what I'm saying here, right, is functions, basically take a series of commands and store them in a location. Now, and I want you to think about this. If I create a function for a program, and then I find a purpose for that function in a different program, all I have to do is copy its code and drop it in, right? When you think about using the print command or the input command, which are already functions built into the standard libraries of Python, where is that coming from? Somewhere there is a Python file that holds those commands and knows how to process the stuff that I send to it in the form of an argument, and it receives it as a parameter, right? So all that goofy terminology. So we need the def keyword. We need to give it a name, optionally send in parameters or arguments, right? The colon has to be at the end of that first line. And then things need to be indented, right? And so that's kind of all the little reminders there, basically. All right, and I want to get to a blank line here, so bear with me here while I'm running out of screen space. Let me go full screen on this. Okay. Before we actually write the code for the program, can we do a little test? All right, and I got a phone call coming in, which is highly convenient. All right. I want to do just a little bit of a test and practice with this, right? So for example, let's just play with a function before we code the program. So for example, if I code a program and I create a function called say hello, right? Notice I'm being verbose with how I name it. Some people will name them like this. Some people will also use what we call camel casing, where if they're using multiple words, the first letter of the second, logical word becomes a capital. It doesn't matter which way you do it, right? As long as you remember what that name is. I have my colon in there at the end of the line, and notice when I press enter in Visual Studio Code, it indents me 4 spaces. On the W3 site, it was just 2. Whatever the indent is, it has to be consistent, and keep that in mind. A tab is not the same as spaces. These are spaces. Right. So now I'm going to type my code. So I have some statements here, like goofy ones like this. So like hello or something like this. And yeah, this is what I did last time. So I'm just kind of reiterating it. And then I might also like do some math or something in here. So like 1 + 5. And then I might also print the number. And the point of this is to show you that you can run multiple commands over and over and over again, right? So this is a really simple function with several different commands in it. I'm not sending any information to it. It's just executing its commands, which is putting stuff on the screen and doing a little bit of math. So if I want to utilize this function, now I'm going back to the margin. You notice I backspaced, and now I can call that function by just simply using its name. And notice Visual Studio Code is recognizing it. I just, type it partially. I do need to put the parentheses in if that's what our indicator that we're calling a function. And you know what? I don't have to run it just once. I can do it multiple times. So I'm going to do it a few times like that. Now I'm going to run the program and watch what happens. So this is just a demo, right? So notice how it's repeating the code. It's doing the math in the background and outputting the answer. And it does it 3 times over, right? But it's easier to type that one command than type all those lines of code and conceptualize. Here it's only 4 lines of code, but it could be 1,000 lines of code. And inside that code, I could be calling other functions Well, calling print is a function, isn't it? Yeah. So this is really kind of cool, right? So if I ever needed this for a different program, I would just come here, copy this and drop it into a different program and I'm all set to go. Just have to call it. But you have to remember, and this is a problem that people have when they first learn functions, is they define them just fine, but then they forget to call it. So it never runs. It's like, I've been looking at my code for hours and it's not running. I don't understand why. Well, you never called the function. You never asked it to run, right? So you notice I'm defining it and then I'm asking it to run. Right, so that's the example. I am going to delete that stuff. All right. So let's just get rid of all that. All right. Well, actually, let me backtrack a second here because I'm looking at my examples from last time and I want to kind of follow them up a little bit. What if I define another function? So I'm just going to create another one. So I'm going to define one called say hello to someone, but this time I'm going to throw a name in there. So my print statement, and I'm just going to copy this just to make it go faster. I'm going to, when I call this, I'm going to have to send in a name and then I can output that name. So for example, if I want to say hello to someone named, whoever, I can run that. It's sending the information in, dropping it in. So it's coming in. This is transporting to here, which comes down to here and executes the task. So that's sending an argument in. Here it's an argument. Here it's a parameter. So the function receives a parameter. The program calls an argument. Right. And if I want, I could run this again. And this is kind of, very simplistic, mind you. I'll call my dog Abby. There you go. And I can run it multiple times. And notice because it adapts to the information being sent in, it becomes flexible because I send different data, it behaves in a different way. All right, let's go ahead. Let's get rid of these examples. And if you guys want to, if you're following along and keeping them, that's absolutely fine. But we have a very specific task that we're told to do, that we basically need to create a function that accepts two parameters and returns the area by multiplying the two parameters. And so we're kind of going to ramp up this concept a little bit in the process. So the first thing I'm going to do is I'm just going to drop in a note like this, for example, right? Just to tell you what I'm doing, right? Because we're going to have more than one parameter. So I'm going to define a function called get area with parentheses. And let's think about, how do you calculate the area of something? Well, it's length times width is the formula, right? So I'm going to send in those values and I'm going to call one value length, a comma, and then one value width, right? So it's going to receive those both. And it's expecting them to arrive in that order, by the way, right? So if this was like first name, last name, I want to send the names in that order. And I'll show you how to send them in. All right, now we need to do the calculation. So there's a couple ways to do this. So I could, for example, set up a variable called area and then just multiply length times width. And then I want to send the result of area back to the program, and I would do a return statement. So the return statement isn't required, but if you're sending a value back, it is required, right? So what am I returning? The calculated area. All right. To run this, I need to go back to the margin. I need to call it, right? So I want to run get area and send a length and a width. So I'm just going to drop in some numbers, 20 and 15. Okay. Now this will run, but I want you to think about what's going to happen here. I run this, this is going to send something back to me. There's no print statement here. What's going to come back? Well, there's nowhere to put it. So I'm going to have to create a variable, and you know, and I'm coming up with a name for it on the fly here. So if a function is returning a value, it has to have somewhere to go. This is kind of interesting. So I could store it in a variable and then print it. So I could print calc area, or the other approach would be I could just run the print statement, call the function within the print statement, and send the values from there. It'll send the values, return the value, drop it in the print statement, and output it to the screen. Both approaches work. All right, so let's run this so you can see it working. Right. So first calculation, sent 20 and 15, length and width, received it here, put it into the equation, stored it there, and returned it. Right. So I called it, returned a value, I stored it here, and I printed it. Or I just dropped it right into the print statement, sent the values, or returned a value right inside the print statement, put it on the screen. Both of those work just fine. Another approach, by the way, some people once again will look at this and go, why are you storing it? You're just returning the value and then it's going away. Interesting. So an alternate approach, and I'm going to comment that one out, is some people, instead of storing it in the variable and returning it right away, they just put the calculation right in the return statement. That works too. So I will run it again and you'll see I get the exact same output. Now, if I don't need to reuse that value in the function, this actually makes more sense. This is probably the better way to do it. Another thing to think about, right, is you're calling the function, you're storing it, outputting that variable, also hard coding it. Both of those work just fine in that scenario. Right. All right. Is this function good enough to complete the lab? First function? Yeah, totally. Yeah, this works. All right. So we're asked to build a different function though. So this is just an example. If you want, you can comment that stuff out. I'm going to get rid of it for now. Right, it's going to be in the video, so it will survive beyond us. But we're also asked to define another function called calc area by input. And this is part of the instructions. And we weren't told to send anything to this. In fact, what we were told is that this will prompt the user for the length and the width. Okay, so here's my prompts. First one, I'm creating a variable called L. To me, it means length, right? If you don't like that, just call it length. That's fine, right? Grabbing the input, which comes in as text, we're converting it to a floating point number and storing it. Same thing with the width. Pretty straight ahead. Right. Now, keep in mind, people that the examples that we were shown, they were typing in a whole bunch of floating point numbers. That's why I chose floating point. We could make it just, work with integers too. And honestly, our formula would work either way. Doesn't matter, because once the numbers are there, they're there. Then we'll go ahead and we'll call the function. We're sending in the length and the width in the order that they expect to be received. We're storing the output in a variable called area. And then we're going to output it. This is all within the same function. So this will handle input, processing, and output, right? So input, processing goes to a different function, but it's processing. And then the output. And then if we want to do this 3 times, we just call it 3 times. And notice, just type 2 letters, arrowing down, pressing enter, set of parentheses. And if you're clever, you copy paste. And there's the call to it 3 times over. So that's all the code for that lab, believe it or not. Very, very simple. Not a lot of code, but there's really a lot of concepts going on here, embedded in these few lines of code. There's a lot of power to it. The fact that I can issue this statement and execute all these lines of code and have it dynamically adjust to different scenarios is very cool. All right, let's do a control S to save, and I'm going to run the console here. So let's use the examples. 2.5 and 2.9. 2.5, 2.9. All right. First calculation is good. 8.4 and 3.6. 8.4, 3.6. Okay, well, that one's messy, right? Is that what we got here? No, that one's truncated. I can fix that, right? I know how to fix that with that 0.2f thing, remember? Right, so we can totally do that. All right. And then enter the last one, which is 3.2 and 5. So 3.2 and 5. 16.0. Great. It looks like these are all set up for 2-digit precision. So we can make that adjustment really, really quick here, which is very simply inside here. We do :.2f. Saving. We'll run it again. And let's put in 8.4 and 3.6. 8.4. Oops. Type it in the wrong spot. Click here. 8.4. 3.6. Much better. Right, so now we're controlling that output. All right. All right, we're going to move on to the next lab exercise. This one's called the change calculator, and this is kind of a neat one for a couple of different reasons, but we're also going to pepper in a new concept here, and that is if statements. So we already looked at the documentation on functions, so I'm not going to repeat that, but the link is there if you want. But one of the essential parts of programming, and this is really kind of an interesting thing to talk about, is when we first learn how to code, everything that we do is a sequence of steps. So like I print something, I input something, I calculate something, I store something, I call a function, but it's all step by step, like making a recipe, right? Like preheat your oven, mix the flour, eggs, and sugar, put it on the cookie sheet, cook it for 15 minutes, let it cool, and enjoy with a glass of milk, right? It's a very defined series of steps. Sometimes, though, when we're writing code, we need to make choices or what we call a selection statement or a decision statement in our code. And we have to ask questions in our code that can result only in a true or false result, or a yes or no, in order to be able to proceed. So for example, if I was making chocolate chip cookies and I got to the point where I'm making the batter, if I also have some pecans, I can add them to the batter and have chocolate chip pecan cookies, right? So if I have pecans equals true, then I can have pecan chocolate chip cookies. Else, I'm just having plain old chocolate chip cookies, right? So you see the logic that goes with that? But when we're testing logic in what we call if-else statements, right? So decision statements in Python, we have to first look at what we call logical operators to determine if something is true or false. So often what we will be doing is comparing one value to another. So for example, we can check, I want you to notice here the double equal sign. Is A equivalent to B? And I want you to notice how I'm saying that. I'm not saying equals. They're saying equals. But when we look at our regular code and we use a single equal sign, that's an assignment statement. That's how you put something in a variable. if you really want to check to see if something is equal, you got to use two equal signs. And I always try to change the way I say it. I say, is A equivalent to B, right? Are they the same value? That could be either text or numbers, by the way. So if both of those things are equal, that would result in true, and I would execute a statement. And if it results in false, I would not. If I'm checking to see if stuff is not equal, the operator that we use is the exclamation equals. The exclamation is what we call the negation sign, which means it flips the double equal sign to a not equal. So this would be true if A does not equal B, right? Then, of course, we have less than and greater than. I think those are pretty intuitive, like 1 is less than 2. So if A is 1 and B is 2, then that would be true. If A was 2 and B was 1, that would not be true, right? We can also throw in the equal sign. So if A is 1 and B is 2, A is less than or equal to B. But if A is 2 and B is 2, is it less than or equal to B? Yes, yes, it is, because it's also equal, right? It includes equal, right? And that kind of trips people up a little bit. So we have both the less than and greater than version of those. These are the most common of the negation or true false statements that we put. So normally how we operate this, is we'll set up values. Numbers are really good to do this with, at least initially. So we check to see, if the statement is true. So A is equal to 33. Well, not equal. A contains 33. A is 33 is a better way to say it. B is 200. Now we check, if B is greater than A, is that true? Well, yeah, it's true. So then this statement will print. All right. Let's just try it just so you can see. So we'll leave the numbers as they are and we'll run it, and it will come back with B is greater than A. Okay. But what if I change A to 333 and I run it? I was thinking on that one for a little bit. Well, we know that's not true. So what's it going to output?
Should be an error.
It's not going to output anything. This print statement, like the statements inside of a function, will only execute if this statement is true. In this case, it's not true, so the statement will not execute. All right, let's keep moving on, right? So they talk about indentation. So when you do an if statement, that is not going to work, right? So that's not part of the if statement. That print statement will print either way, or you'll get an error because you never gave it an indented statement. Now, we talk about if else, and at the very top of the page even they say if else, but Python is weird. So this is how they do else if in Python, right? So if I want to test a second statement, we say Elif. Really weird, but that's how they do it in Python. Right. Let's try this one out. This is kind of interesting. So in this case, A and B are the same. So is B greater than A? Nope. Else, if, right, Elif, A is equivalent to B, then it will output that statement. All right, so want to test it? Let's make B less than A. What's it going to output? B is not greater than A, so it's not going to do the first one. A is not equal to B, so it's not going to do the second one. So it's going to do what? Nothing.
Nothing.
Yeah, it's not going to do anything at all, right? As proven there. However, if I make B greater than A and I run it, the first statement will hit, the second one will not.
Right? I have a question. Why doesn't it produce like an error at all? Is there a reason?
What error would it produce?
Not sure.
I know where you're going with it, Anthony, because it's like, well, if this isn't true and that's not true, what does it do? It doesn't do this and it doesn't do that. What happens next? There is no next.
Okay.
So if so, for example, um, this is next. So if okay, so in this scenario they're equal, but if I make the statement once again untrue for both, only that statement will print. But at
Okay.
least something will print. There's no error here.
Mhm.
Neither condition was met.
We have to code it in saying, hey, neither is like
Yeah, precisely. Yeah. Now you're kind of getting it. Now there's also the else, right? And the else is like will happen if none of the conditions above it are true, right? So in this case, A is 200 and B is 33. Is B greater than A? No. Is are A and B the same? Mm-mm. So this is what we'll print. Now think about this also. We're not testing if A is greater than B, but that's the only logical option that's left, right? If B is not greater than A, and A and B aren't the same, then A must be greater than B. That's why we can even put the statement here. Another thing that you can do, and this really isn't stated here, right, is we don't have to have an else if. We can just go if and else. So if B is not greater than A, then A must be greater than B, right? I don't have to test for it because that's just what it is. Right? So these are if statements, and I know that this is a very simplistic example of this, but if statements are hugely useful because think of how many things that you do where you need to make decisions that are driven by information or data. So for example, one of my favorite ones to do in all my programming classes, Anthony, this will bring like familiar, like I want to have pizza for dinner tonight. If cash in pocket is greater than $20, I'm getting a pizza from Ian's. It's right down the street, right? Else, I'm making mac and cheese, right? Because I don't have $20 to get the pizza delivered. Caleb?
Yeah, so if you were to change A to 33, making them equal, would it then print A is greater than B? Because it's not testing then?
Yeah, it wouldn't. Yeah, it would definitely output that. Not that the output is correct, and really it should be
Right.
reworded. A is either the same as B or greater than B is really what it should say. Right, but we control that output. It's not based upon an actual test. But yeah, that's an excellent question. All right, let's go ahead and get some of these examples out of the way here. Free up a little memory. And let's try to build this change calculator. So we're going to create a calc change function that does the following. It takes one parameter representing an amount of money. Then we're going to calculate and output the least amount of change using the following denominations: dollars, quarters, dimes, and nickels. Pennies too, I guess. If a denomination is not used, we do not display it. Okay, this is a little bit more challenging problem because this is going to get you to think like, all right, how am I going to accomplish this? And this is kind of one of the ways that programmers think, by the way. You don't like just rush in and write the code typically in a situation like this. You have to think about what might be the process for doing this. Now, if we were, let's say we were working retail and we were the cashier, right? And this is one of those things. So you walk in, I'll give you a scenario. You walk into McDonald's and you order a sandwich and the person says, that'll be $5.14, please. And you have, you don't have a $5 bill, but you have a $10 bill and 14 cents, right? Most people would give the person the $10 bill and then they type 10 into the register, press enter, and it tells them how much change to give the customer, right? But you can throw the person for a loop. And I don't do this intentionally to cashiers, but just because I'm kind of used to old school retail, I would give them a $10 bill and the 14 cents. So I get a $5 bill back, right? But if the person already typed 10 into the register, they sit there with a blank stare going, I don't know how to give you change, just take the 14 cents back. I'm like, I don't want the 14 cents back, you know, that kind of thing. And this is really kind of an interesting problem in a lot of different ways because it explains why we develop certain aspects of logical operators in programs. So for example, like why do we have modulus as a mathematical operator, and why do we have floor division as a mathematical operator for a programming language? And it was this exact problem that forced it to become a reality. And I think that's really kind of fascinating because when you have to go through the process of making change, you think about this, you have to think about like, what money am I giving them back? What's the most efficient way to give them that money back? So if you're getting, for example, 83 cents in change, what's the most logical way to get that money back? And so here's kind of how I'll demonstrate this, right? So, all right, so you give, you buy something, it costs a few pennies or whatever, you give them $1, say it costs 17 cents, and you give them $1, and they have to give you 83 cents back. Okay, how do you break that down? Okay, well, I worked retail for a really long time and without a cash register, right? So I know how to do change without even thinking about it. It's just like kind of automatic for me. But a lot of people don't these days because nobody uses cash anymore, right? And nobody likes math either. But the logical way to do it is, well, I'm going to give them quarters back first, right? Because that's the largest coin I have. So I'm going to take that 83 and I'm going to divide by 25. That's only going to go in there evenly how many times? 3 times, right? And so really what we're doing is floor division, right? So we're dividing in, we get a whole number response. We don't get the remainder or the fractional portion, but there is a remainder. So like the way that we get the remainder is we take the 83, and instead of using the floor division or regular division, we use modulus, we use the percent sign, and then we get the remainder. What's the remainder if I divide 25 and 83? Okay, I know, quick, 8 cents, all right? Because 3 quarters is 75 cents, there's 8 cents left over. All right, so now I have 8 cents, that's my remainder. I got to make change with that. Can I divide a dime into 8 cents? Nope, doesn't work. So that one's off the table. We don't display that one. But now I want to take that 8 cents. I can divide a nickel into it. How many times does that go in? Once. Okay. How much is left over? Right. Well, you would do the modulus on that too. So you would, in programming it, I mean, in your head, you already figured it out, but in programming, we would write out the equation and we would have what left over? Wait, that would be a 5, sorry. Put the answer there. All right. So we'd have 3 left over. Now we take the 3, and what can go into that? Well, pennies can go into that evenly. So we have 3 pennies. So the change then is 3 quarters, 1 nickel, and 3 pennies, right? And this is interesting, right? Because it explains why floor division and modulus exist, because it came out of a very practical problem. Explaining how do you make change. And I think it's a really kind of neat little problem. Notice we skipped over dimes, but if it was appropriate to use dimes, and this works in any scenario, so you divide, floor divide, and modulus divide by each denomination, just working downwards until you get to where you need to be. That's the algorithm for this, So why does it say use floor division and modulus? This is why. Okay. So I'm going to wipe that from the screen, but I think that's a helpful little explanation as to how the logic works. Now we got to convert it into code, which is a whole separate little scenario. All right. Pulling out my cheat sheets here on screen number 2. We're going to follow the exact same procedure to do this. And oops, let me get my little annotator on here. So I'm going to create a new program in the same folder. I'm going to call this mod2 lab2 dot py. And another kind of weird thing is because we are asked, if you look at the instructions here, that we want to build a function called calc change. Right? So I'm going to go ahead and start defining it. And I want you to notice I'm starting a few lines down. I'm doing it on purpose. So I'm defining calc change, parentheses, and a colon. All right. Now, to calculate change, I am going to need to send in a parameter of whatever the monetary amount is that I'm going to calculate change for. So I'm going to just call it amount, whatever that is. Right? And then I'm going to, put code here. Put code here. But I'm going to put the brakes on for just a moment. There's a convention that we use in Python too. So like if you start writing programs that have a lot of functions in them, and then you have other people that you're working with, that you're writing code with, and they're looking at your functions later going, what the heck was this person doing? Right? It's really polite to explain what your functions do in the form of comments. So there's this kind of convention that Python programmers use that kind of looks like this. So for example, they'll put several lines of comments above their function as they're building it to describe to other programmers what they're doing. So when they look at what does calc change do? Oh, it says right there what it does. So for example, I would, tell them what it's called, tell them what it does, right? And then the other convention is if it receives a parameter or an argument, you use this little param thing and you say, you list all the parameters that you're sending in. It's not very good English, but you get the point, right? So when somebody looks at this later, they can go, oh, what does the calc change function do? Oh, it calculates the most efficient amount of change for any dollar amount. What parameter are we sending? Oh, the amount of money we're trying to make change for. Okay, I got it, right? And if you have multiple parameters, you list each one and what that is. If it does more than, this, you state it. You tell people what it is. And that way, what you're really doing is you're kind of creating a little descriptor for your function. Interestingly, if I, for example, put in a print command in a Python program, do you notice how it pulls up like all this information? Where do you think this information comes from? It comes from comments like this built into the library that holds the print function. That information is embedded, right? It doesn't come from nowhere, right? And so that's kind of like the general point of it. Notice if I hover over the function that I've created, it also kind of gives me a little bit of information. It doesn't read that description, but that can be forced, by the way. And I think this is really kind of interesting, where some of this stuff is derived from. All right. So the first thing that we're going to do is inside the function here, and I'm going to come back up to the first line, is we're going to prompt, I guess, the user. And I'm trying to look at my previous example here. Apparently, we're gonna prompt the user somewhere in the program. So let me kind of do this first. I'm going to come back to the margin and come way to the bottom, and I'm going to begin with the last line of the program, which is this. When the program runs, this is what's going to happen. I'm going to call my function. I'm going to prompt the user, enter an amount to make change, right? And convert it to a floating point number. Since I'm calling a function with this, it's grabbing it from the user, turning it into a number, and then sending it here for processing. The function will handle the rest. Okay. So up here, I want to first confirm that the amount that's being sent was received correctly. So I'm going to reiterate it on the screen. So the user typed $2.59. And so I'm just going to say change for $2.59. Okay. So just repeating the information back on the screen. It also confirms that I got there okay. I'm going to leave a blank line here in my function. That's okay. You can do that. The indent's consistent, but I'm going to do that. All right. So the algorithm that we used before, we started with quarters and worked our way down. But if you notice that the program description also said we got to deal with dollars too, right? So I'm going to create a variable called dollars. And then we're going to do our calculations. We're going to take the amount they're sending in. We do floor division first. And what are we dividing by? We're dollar bills, single dollar bills. Okay. Now notice, is this okay? Can I divide the floating point number by an integer? Is that going to work out okay? Yeah, that'll be fine. Right? Plus a dollar bill is $1, so that makes sense. All right, now let's go ahead and take that amount. Okay, so actually we need to experiment with this for a second. I want to show you what happens here. If I print dollars after this, so let's run this and see what happens. So if I type like $5.32, or $4, let's make it $4.32, and I'm trying to make change with that. What is that division going to do? So Caleb, this kind of goes back to your question from earlier, right? Like how did these numbers kind of scale out? Right. Control S to save. Here comes the run. Enter an amount to make change. I'm going to do $4.32. All it's going to do is divide that by 1. But I'm doing floor division, right? Okay. So it goes in there 4 times, but it does convert it to a floating point number. Okay. Is that all right? Yeah, this is where it gets a little weird. Often if we're working with dollar amounts, all right, let me experiment. Let's just do regular division and run this again. Let's put in the same value. Interesting. Now, what I'm doing here is I'm trying to explain why we're using floor division, because okay, the change for $4.32 is $4.32. By the way, right? Because if I divide 1 into any number, what's going to come back? The number, right? What I really want here is the number of dollar bills, which, once again, if I run it, $4.32. Oops, sorry. Here, $4.32. Okay, 4.0. All right. The 0.0 is not relevant here. You see this? Right? I just want to know how many dollar bills I need to get them. So really, I should be basically rounding that down. And I want to round it down. All right, so this gets really weird, but I'm just going to throw this equation out there, because sometimes what happens when we do math in a programming language, by the way. So I'm gonna comment out this statement, because we're not going to actually use it. It was just to demonstrate. Is I'm going to take the dollar amount that's going to be left over, and I want you to think about this, and I'm going to mod it by 1. And then I'm going to use this to round it to 2 decimal places. So I want you to think of what's going to happen here. If I take $4.32 and do modulus on it by 1, how many times does 1 go into 4? Well, it goes in 4 times. But modulus is looking at the remainder. So what is this going to give me? The 32 cents is what this is going to give me, right? And we're using the round command because if I don't, it will give me the wrong amount. And so the only way I can really demonstrate this is to show you. So if I do, let's kind of get rid of this and that. Let's just put in that. So I'm going to take the amount, do the modulus, and then we'll print the amount. And this maybe will help it. We don't want it as a comment. I'm going to print. And then we're going to talk about the why this happens. And this is a really weird thing with programming, by the way. All right, so I'm going to put in $4.32. It's going to calculate the dollars, and it's not going to do anything with it. But then I'm going to take the amount and mod it by 1, hoping to get the 32 cents. Watch what happens. Okay, that makes no sense if you think about it mathematically, because if I did this with pencil and paper and a regular calculator or a spreadsheet, it would give me the correct answer. So why on earth is Python, well, the 32 is right, but where's this 0.0000 whatever 3, right, coming from? Okay, this is what's going on. When we work with numbers, we work with a base 10 number system. The base 10 number system has 10 possible values, 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? When computers work with numbers, they have only 2 possible numbers they can work with, 0 and 1. So when I type in a base 10 number, the computer somewhere, somehow, is converting that into a binary number, in principle of the same value, doing the math with it, and then giving me back the result. But in the process of converting to binary and then converting back to base 10, we have what we call rounding errors. So when I do this command, right, and I'm going to put this in, we do this command, why do I round, and force it to be 2 decimal places, it's to truncate this error. And all of the mods that we're going to do are going to contain that to remove that rounding error, because otherwise this will not work correctly. So, you know, this is a superfluous command just to prove it, but let's run it again. This time you will see that now we've been able to control that. So 432 will give me 32 cents remainder. That's correct. All right. So that pattern then, so these 2 print commands are just for testing, so I'm going to comment them out, but the pattern is whatever the denomination is, mod by its value, that's going to be okay, right? The whole number part's going to be fine, the floor division. When we do the modulus part, we have to get the rounding thing in there. Otherwise, we get the binary conversion error, unfortunately. Weird, but wiring minds want to know. And this is it's not an error, by the way, right? This is just kind of how programming languages work. When you're working with a calculator, the calculator is making the same mistake, by the way, but it's got software or logic built into it that never shows it to you. Now you're working with a programming language where it's not obscured from you. And if you don't know how to navigate it, you got to deal with those extra digits. Right? Well, think about this. So if I was trying to land a man on the moon and that was like my trajectory formula or something like that, that 0.003 might make him miss the moon. Right? So we want to fix those kind of errors, basically. All right, let's move on to the next thing. So first, we process the dollars. Then we're going to do quarters. So with quarters, and you notice I'm naming the variables what they are. We're going to take the amount. Now, mind you, this is the 32 cents now, right? We're going to mod it by what? 0.25. That's the value of a quarter, right? Then we're going to mod the aftermath, right? So we're going to take the amount. We're going to run that same round command, but we're going to adjust the value so that we're modding by 0.25. So that's for quarters. Now, if you want, and this is, if I was writing a program where I'm doing calculations like this, and they're really important calculations, every time I would add a statement, I would drop in a print command and test it to make sure it's doing it correctly. How many quarters should this calculate? It should be 1, right? And then what's the remainder? It's going to be 7 cents, right? So I could write a print statement here and a print statement after that to test it. I'm not going to do that here, but maybe I should. Maybe, I'm talking about it so much. So do programmers really do this kind of stuff where they like just put in print statements to see if their stuff is working correctly as they're building it? Yeah, totally. We totally do that. I want to make sure that what I'm doing is actually working before I move on to the next step. So I would save this, I would run it, I would put in my $4.32, right? So one single dollar. All right, so we probably have to fix the outputs of this, but, and then there's 7 cents left over. That sounds right, right? And actually, what does this represent? Because remember, we're not printing this stuff. It's not the dollar anymore. 1/4 and 7 cents are left over. All right. So just proof that that's working. And once again, I'm going to comment those out rather than delete them. But that's like testing in progress, right? And then, if you do a whole bunch of that weird testing, you can go back later and just delete it all. It doesn't have to be there. It's not really part of the solution. It's part of the building process. All right, so next we'll do dimes. Dimes equals the amount modded by 0.1. If you want to go 0.10, that's fine, same difference. And then we'll take the amount, and then we'll do a round, and we'll take the amount, we'll modulus by 0.1, and round to 2 decimal places. And then, of course, you want to save a little bit of time and speed up the process here. There's this thing called copy paste, this wonderful thing. Nickels, we'll change that to 0.05, change that to 0.05. And then we'll do pennies. Okay, well, here's kind of the discussion. When we did the algorithm before, right? With pennies, well, pennies will divide into anything, right? It doesn't matter. So we don't have to modulus that one. We just have to change that to 0.01. There's no modulus part to that equation, right? So kind of reviewing the whole thing here, and I'll close the console, and then I'll blow away the comments, right? Just to make it more concise. So there's the statements. Floor division by 1, mod by 1, round it. Floor division by 1/4, mod by 1/4, round it, et cetera, et cetera, et cetera. We get down to the pennies. We don't need to mod that because that will go evenly into anything. Then we need to start asking some questions. So here come the if statement. So here's the if part of the process. All right. So I'm going to write if statements that are only going to display how many dollars, how many quarters, how many dimes, how many nickels, if we actually calculated any of those things. So if we don't need nickels, I don't want it to show. All right, so watch the logic I do here. We'll start with dollars. I'll say if dollars is greater than 0. So if there's some dollars, right? Then what are we going to do? We're going to print, and yes, I'm copy pasting. So I'm doing string interpolation. I'm putting dollars inside of curly brackets. And notice I'm rounding to 0 decimal places. I don't want it to go, how many dollars? 1.0. I don't want it to do that. I just want it to say 1. That will basically drop all the floating point stuff off. We're going to follow that pattern. Notice when I pressed enter, I'm still indented, so I'm backspacing 1 and writing a new if statement. And you can maybe guess what might come next. So if quarters is greater than 0, and yeah, I'm just going to do a little copy paste in here. Might be 1/4, could be 2. That's why the parenthesis S. And I suppose that would probably be appropriate on all of these, honestly. Could be $1, could be multiple dollars. We don't know. I'm going to keep moving on this. So from quarters, we go to dimes. And I'm trying to be careful with the indents here. Right. And I know you guys are probably hustling to try to keep up with me. And I'm cheating by copy pasting, sorry. I'll be here all night long. If there's nickels and pennies, it's all the same logic, right? As long as we have some, we will display it. Notice none of the if statements have an else or an else if. They're not appropriate. The point of this is if we have calculated that we need some of these, there's more than none, then we will output it. If not, we don't output it. Right. And the last thing I did in my function, which is a little weird, is I just put a blank print statement, blank line at the bottom. And there's a reason for that. That way I could test it multiple times over. So there's all the if statements. So I don't know if you guys are screen capture or whatever, you know, or trying to type super fast. I'm trying to keep talking for a while so you can keep typing. Yeah, I know. The strategy, right? All right. So now I want to test. Yes, please.
I have a question. So
Yes.
I'm sort of following along, right? And I'm sort of going ahead. And when I added the round function in, I didn't get that answer. I got the answer. If I'm jumping ahead, catch me.
All right. You know what? It could be. So Anthony, I feel where you're going with it, right? So, and I know you have a little bit of coding behind you, so like, you know, you're proceeding in that fashion, right? Just make sure, like when you're doing quarters, that both of those values are 0.25, dimes are both 0.1, etc.
Okay.
That could be where it's hiccuping.
I'm just trying to see.
It's easy to miss that, honestly.
It looks correct, but yeah,
right.
My output didn't come out the same when I added the round.
All right, let's remember here that I already have a prompt down here that will call the program, right? So I'm going to start running this, and I'll be real frank here, right? So this is prompting the user to put in whatever amount they want. But what a programmer would do, you know, is they would test their code with just really primitive function calls like this. So like before you go prompting a user, let's just make sure it works. So I'm just going to call the function manually, not prompting the user, and I'm just choosing a value and throwing it in there. Now, being the, I guess, retail aficionado that I have been in the past, right? Okay, I would, for $2.59, I would give them $2 bills, 2 quarters, a nickel, and 4 pennies, right? Yeah, blank stare from all the young people, old people, like, that's right. Don't worry, you'll get us back with the next lab. You can call us all boomers. So, all right, let's run it just like that and see if indeed that it does that. $2, 2 quarters, 1 nickel, 4 pennies. Spot on. Okay, let's try a few more values. All right.
I have a question.
Yes.
So I'm running into like I don't know if it's like a weird rounding issue or not. Like I'm using round and everything and but like for instance when I type in like $5.68, like instead of 3 pennies, it's saying 2 pennies.
Okay.
But when I did the one that you just did, 259, it said 4. So it was right for that. So I
Okay.
don't know.
Hang tight there. Let me
Okay.
run these examples and then we'll come and take a look at that because it's probably just a little syntax thing,
Okay.
but we'll troubleshoot it together. And it's a really good exercise when something's not working to collectively look at it and try to figure it out. Right.
Okay.
So I want you guys to notice here, now I'm throwing a bunch of different values at it. And then for each one, it'll list the amount and then we can verify that it's doing it correctly. All right. So let's run these. So I did 378, $1.11, and 23 cents. There it goes. So the first one we already confirmed. 378. Okay, $3, 3/4. Ooh, 2 pennies. Ah, yeah. Okay. Alexis is on to something here, right? Yeah, that's not right. All right, that's not right. All right. This one is right. Dollars, dimes, and pennies. That adds up to $1.11. For 23, 2 dimes and 2 pennies. That one's also wrong. Uh-oh. All right, I want to quit and go home now. All right, that's what you guys are saying. All right, so these are really weird little mathematical issues. So let's try to figure out the why. All right, let's try to figure out the why. All right, let's break down the logic here. When I get past this point, this is probably where it's breaking. All right. I have a wonderful idea. Let's do this. There is an answer to this, but I want you guys to think about it for a little bit. I'm going to pause the video. We'll take a 5-minute break, and when we come back, we'll talk about the solution. But meanwhile, if you're so inclined, see if you can figure out a logical reason why this is happening, because there is a logical reason why this is happening. It might have to do with the rounding. Just kind of giving you that heads up. All right, pausing the video. All right, so we were noticing that some of these answers were incorrect. So some of the penny amounts were right and some of the penny amounts were wrong. And really what's happening, and I wanted to test this, is once we got past the nickel amount, everything worked great up until that point. So I wrote just a really quick little print statement here, and notice I said pennies test to see what was left over. And then I thought to myself, oh, okay, this is happening for the same reason that we're using the round command. We're going from binary to base 10, or actually we're going from base 10 to binary and back to base 10, and the conversion messes things up, especially when we're dealing with decimal numbers. So here was my fix. And I am removing this statement, but I put it in there to test. And I'm just going to put a note, did to test fixing the pennies issue. All right, so I remember. And so what I did here, when we got to this point, this would basically display whatever pennies are left. So it's going to be, think about this, between 0 and 5 pennies, right? Or 0 and 4 pennies technically. To correct the rounding error, I just took that penny amount, multiplied it by 100, so it scales correctly. Then instead of dividing by 0.01, I'm dividing by 1, and then all of a sudden the problem is resolved. So Alexis, I'm glad that you noticed that. So let me just run it really quick and see if it fixes all of them. Here's the run. So that's correct. That's correct. That's correct. And that's correct. All right. And I see you have your hand up against question.
Yeah, so I guess like at that point though, why would we not be able to just instead of having pennies at all, just like do amount. Just print
But
amount straight up.
that's a really good point, right? And maybe I'm maybe I'm overthinking this because um, what's the amount that's left, right? Yeah, you're right. So like basically, if I take the amount, multiply it by 100, and then floor division by 1, isn't that the same as just saying the amount? That's what you're saying, right? So I could, instead of here outputting pennies, I could just output amount. Is that what you're implying?
I guess I was kind of implying like we don't even need the variable pennies at all, but you'd still need the if statement. But I guess you would just want to say like, um,
Yeah, that
I mean, I
that
guess I
works too.
see why.
Right.
Yeah, I see why you need it there. But like amount, yeah, amount would just give you the exact
Yeah,
same
it would
thing.
just give you that, but I am multiplying by 100 to make it scale correctly because otherwise it would be point zero whatever. So really, I could skip this, right? Or I could just say pennies equals amount times 100. I don't need to do any division at all.
Yeah, I think that's probably more what I was getting
Yeah,
at. Because like you need pennies for the if statement,
yeah,
but like, yeah, okay.
yeah. You know what? I think let's call that. So this is one of those, okay, goofy things where like most people don't want to think about math or programming in this way because it's a logical problem. Um, and it took me a moment to recognize it. Right, you don't need to do the math to do that calculation because after you've put the nickels in there, all you're left with is pennies anyhow, but in the form of point zero whatever. So I just multiply by 100. That tells me how many pennies I need as a whole number, and we're done. There's no division necessary. So Alexis, a very, very astute observation. Um, and let's call this the best answer. All right, so here's what we'll do. I've run it a few times to test it, but now let's do it with allowing a user to input any amount, right, rather than amounts that are canned. And that will be the true test. So I have my prompt all set to go down here. So let's get that active. Control S to save. And don't worry, I will display all the code again. And now we can come up with any dollar amount that we want. I'm just going to do like $7.93. That should be a good. So $7, 3/4, 1 dime, 1 nickel, and 3 pennies. Correct. Right. Let's keep running it a couple of times and try to break it maybe. How about $5.10? Notice $5, 1 dime, no quarters, no pennies, no nickels, right? That's all correct. Right? It seems to be working. And what I would say is I would challenge you guys to like test it in a bunch of scenarios. And if you find somewhere it's breaking, that's indication that we need to fix it. All right. So for those that are screen recording or actively screen capturing, here's the top part of the code. Right, with the mods and the floor divisions. Here's all the if statements and all the test runs.
Could you do me a favor? Could you go back to the top?
And then the prompt at the bottom. All right, I do see that I have questions, so I'm going to go ahead and pause here for just a second. All right, we're going to move on to the next lab exercise here, folks. And I might hit a video here, so if that happens, I apologize. We're moving on to lab 3. All right. So this is the one where you guys can poke fun at us old people, right? Or most specifically me, I guess. All right, so we had a couple things to look at here. I think we've talked about most of these topics. We looked at else if statements already, so I don't kind of want to repeat that stuff, but we're going to use them here. And they do want to talk a little bit about logical operators, right? So there's math operators, which we've been playing with. We've now used all of them in programs, by the way. We have assignment operators. We will do a whole thing on this, but we have our comparison operators, and these are the ones that we're going to focus on because we're building if statements. And with if statements, these are important, right? So these are ones where we do comparisons, like, the stuff we just talked about, right? A is greater than B or whatever. But we also have logical operators too. And these are kind of weird because sometimes we write if statements and we're testing for true and false. And we need to check more than one condition at a time in order to make a determination. And so we have these operators, and I want you to notice they're just plain English words, right? And the first one is the and the and is a very simple one. So I might check a condition where I'm checking to see if X is greater than 5, or excuse me, less than 5, and if X is less than 10. Both conditions have to be true in order for the whole statement to be true, right? X has to be less than 5, and X has to be less than 10. So it tells you the number is 4 or smaller, right? All right. The or keyword is a little bit different. Only one of the statements needs to be true in order for the whole statement to be true. So consider this. If I input the number 4 as X, X is less than 5. That's true. But X is not less than 4 because it is 4. Right? It's equal, but it's not less than. But with an or statement, only one of the statements needs to be true for the whole statement to be true. They don't both need to be true, just one. That's a little weird, right? But it's all about logic. The other thing that I'll tell you is usually when programmers write statements like this, they'll write 2 statements, maybe 3 statements. So this has to be true and this, right? They're all ands. They usually don't go beyond 2 or 3. If you're finding yourself going, this could be true, or 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 this could be true, you're probably a more efficient way to do it, by the way, right? So this is a little bit of a mind bender when you're trying to figure out logic, but you have to think about the scenario that it applies to apply it correctly. That's what I always tell people. There's also the not operator. So for example, if we go back to our original example, let's say I input the number 4. 4 is less than 5, that's true. And 4 is less than 10, that's true. But I'm looking for the opposite of that. I'm looking for it to not be true. The not put in front of it negates the whole operation. And there is another way to do this. You can, in other languages, we put the exclamation sign in place of the not, because the exclamation sign is also the not operator in many languages. Here we actually use the word not, but notice how everything's in parentheses. So for example, if I put in the number 11, right? That means this is not true. This is not true, right? So the opposite of it not being true is true. You guys wrap your head around that. This is the opposite of what you're thinking. Right? That's a pretty weird scenario. I usually try to avoid writing code like that, but there are scenarios where you're working with stuff that's already given and it makes sense to do it. But this is kind of the point of the lecture here are those not, ands, and ors, right? So we are going to use a collection of, operators like that, and we can do it, and we can do this a few different ways. And this is why I want to show this to you, and I'm going to show you the different ways to do it. And then I'm going to show you what I think is the most efficient way to do it, which is not the way you probably think it is. Right? And this is where the mind bender is. This is all about logic, right? And this is one of the most challenging parts of programming is, and I want you to mind these words really carefully, because what programmers will do is they will put in their head, well, this has to be true and that has to be true, and I'm going to write my code that way, and that's the most efficient way to do it because that's what my brain is telling me is most logical. But the way that our brain speaks to itself and the way we speak to other human beings is not necessarily the most efficient way to do things. It's just the way that we're comfortable in doing it. And I'll explain exactly what I mean. So basically what this program is going to do is we're going to determine what generation somebody belongs to based on their birth year, right? So some of you might be Gen Xer, some might be Gen Y or Gen Z or millennials or God forbid something else. that I don't know the definition for yet, right? They're still inventing that one. Or if you're really scary, you'd be a boomer like me, right? Because I think everybody else that comes from like the greatest generation is either dead or dying already, and probably is not taking a Python class, or probably smarter than that. All right, the generational definitions are these, right? And yes, I do fit into the baby boomer category. Unfortunately, I caught the very tail end year. So if you guys want to calculate my age, there you go. Secret sauce is out. Right? Now, I'm not embarrassed of it. I feel good at my age, so I'm totally cool with it. But when you would write code like this, what we're going to send in is we're going to write a function called get generation. We're going to send in a year, and then it's going to go through a bunch of if statements and else if statements to figure it out. So the way that most of our brains are going to think is going to be like this. This is the problem solving our brain does. It's going to be, all right, if the year is greater than or equal to 2013 and the year is less than or equal to 2025, then we'll print alpha. So you see how I said that? And that code would totally work. And I'm going to write that code just like that. And then you would just go on down the line and you would make the same statements for all of these year ranges. And then I'll show you how you can do it much easier with no ands at all in the statements, right? So that's kind of my grand goal. And the logic that follows from this is not one that is intuitive. It is one that's learned through practice, right? However, coming up with the long-winded way of doing it, which is how your brain does it, is okay to start with, and it will still work. What I'm going to tell you is it is not necessarily the most efficient. And Alexis, thank you for clarifying. So we have betas. Okay, so we've got alphas and betas. All right. Well, you know what? Thank you for throwing that in there. Wow. It makes me feel old when I'm at the bottom of the chart, by the way, and someday, mark my words, you guys will all be there too. And people will call you alphas or whatever, your designation is. All right, so let's get into this. We're going to do a very simple prompt on this. What year were you born? And it's just going to spit back what you are. That's the whole program. All right. So let's go ahead and get into VSC here and start coding. I'm going to create a new file. I'm going to call it mod2 lab3.py, and we shall begin. All right, so first step is we're going to build a function, because that's kind of the grand goal of the day is functions and if statements. So we're going to define a function that's called print generation, right? Parentheses, a colon. Inside here, we're going to send what year a person was born. So we'll just call it year. Somewhere way down at the bottom of the program. So I'm going to type enter here. I'm just putting in a temporary thing there just to come back to the margin and do my prompt. So this is going to be my prompt, right? I'm going to type this. I want you to notice that this is going to run the function and it's going to prompt a user for a value. Now it's highlighting red. Why is it highlighting red? Well, let's hover and find out. Expected indented. Okay, so it's expecting it to be up here, but it's not. All right, we're going to fix that, so that's not a big worry. Let's start with our logic. So if the year is greater than or equal to 2013, we're not going to worry about the betas for right now, Alexis, if that's okay, because I don't have that code written. I mean, it's easy. It'd be easy enough to add it in. But I didn't even know that was a thing yet. But you would figure after alpha, there would be a beta. And so if 2025 is a beta, then we could switch this to 2024, right? Right. Okay, let's do that. So notice, okay, so the year has to be greater than or equal to 2013, and the year has to be less than or equal to 2024. And then we'll just print. We're just going to make this really, really simple. We'll just say alpha. All right, that's the first scenario. Okay, if that scenario doesn't stick, now notice it is checking one condition for truth and another condition for truth. So both have to be true for the whole statement to be true for that to work. All right, you know what? Let's test it. All right, I know this is dumb to test it now, but is it? All right. I'm going to enter a year. I'm going to put in a year that I know is in there, like 2015. Alpha, it works. Let's run it again. Let's put in a year that's not. And it gives me nothing. Okay, that's right, because there is nothing defined to return. Okay, so we're proving that it works. Now we just have to ramp up our logic, right? So I'm going to indent here. I'm going to do an else if, and then I'm just going to do the next set of years, and you can look at that chart on the page. But so if the year is greater than or equal to 1997, and the year is less than or equal to 2012, oops, that apparently is a Gen Z. And I'm going to guess a lot of you are younger people here are Gen Z. Is this a fair guess? Okay. Yeah, well, I know. So we wish we were Gen Zs. I always find it interesting when I teach classes and I ask people, what year did you graduate high school? And they're like, 2023. You know, I'm like, oh man, I feel old. Yeah, I graduated last century, last millennium, actually. Right. So you can just keep ramping up this logic, and all you're really doing now is you're taking the years in the chart, right? So there's the millennials. There's the Gen X's. There's my sad group. I'm a boomer with a Gen X mindset, I think. It's really probably more actually I probably have a Gen Z mindset, but hey, whatever. And then I'm going to throw in an else at the bottom. Just, I mean, okay, maybe you were talking to my mom. She was born way before 1946, right? And she's still alive and kicking. Right. So hey, you aren't part of any of these generations, and you could be cruel and say you're really, really old, or your generation hasn't been born yet, right? But that should cover it, right? So any year that we put in should work. And what we should do at this point, and here's how I'm going to do it. I'm going to prompt, how many scenarios do we have? 5 scenarios. So I'm going to prompt 6 times, right? So I don't know how to do loops yet, but we'll get to that too. But I'm going to prompt 6 times, put in stuff in all those ranges, and then hopefully it hits on every one, right? So let's go ahead and run it. And maybe I'll zoom out just a little bit here. All right. Here's the run. Enter a year. All right, we already tested the first one. Let's do it again. 2019. Okay, let's do 2001. Both of my kids are Gen Z, by the way, if you're curious. Let's do a 1990. That's a millennial. And then let's do a 1973. That's a Gen Xer. And then let's do 1963. That's a boomer. And then we'll do like something really old like that. And you aren't part of any of these generations. So all of them hit. If you're really truly testing this, by the way, I would also test all the boundary numbers. Like, for example, I would test like, 1965, and I would test 1996 because they're right on the edge, just to make sure they're hitting correctly. But you notice how we're declaring a range here, right? We're going from 1965 all the way up to 1980, This one's set to greater than or equal to, this one's set to less than or equal to. So we're creating a range on a number line, and we're covering all the scenarios. And it works, right? Totally works. However, right, so here's the however. This is not the most efficient way to do it. However, it completely works. Because here's why it's not the most efficient. Every time I'm testing a scenario, I'm testing two things to come up with one truth statement to execute a statement. So I'm testing twice. So it's two processes that are happening that are going through the CPU. Right? All right. I'm going to comment out this code. And I want to show you a different commenting technique here. If I do 3 double quotes in a row and 3 double quotes in a row, this whole block now is a comment. And I'm just going to put in a thing here. It says, this is a block comment done with 3 double quotes to open and close. All right, so it comments out a whole block of code. So I'm going to show you the other way to do it. You don't have to copy this approach, by the way. I'm going to paste the whole solution in at once, right? And you guys will hate me for that because, hey, that's not fair. Right? It is fair because I have the code, so I can do it. But I want to show you the different logic here, and this is really kind of weird, but I want you to think through this as I kind of explain this. And why does this work? Okay. All right. So if you're an alpha, anything that's greater than or equal to 2013, now of course there's the betas, but we don't have that in the mix right now. But is it true, if you exclude the beta thing, that any date that I put in that's greater than 2013 will be an alpha? Greater than or equal to? Yes. All right. If it's not greater than or equal to 2013, then it will drop down to the next one and greater than or equal to 1997. Well, we know it's not an alpha because it's not greater than that. Greater than or equal to 1997 is a Gen Z. Do you guys see the logic here? Now I'm only testing one thing and it still works. Now there's a catch to it. The catch is the direction of the sign, right? And then I'm working from the largest values down to the smallest. So as long as I keep that pattern going, it works. If I put the boomer thing at the top though, right? And I typed in 2015, it would say boomer, incorrect. The only reason this works is because I'm excluding the bigger values as I go down. I could also flip the logic. Here's the flip to it. I could start with the boomers at the top and switch it to less than or equal to 1964, right? And do all the signs in the other direction and use the larger value in the range to do the determination and work from, smallest to largest, and that would work too. This type of logic is not one that entry-level programmers see right away. Experienced programmers, encounter these types of issues and like, oh, or I could do it this way, right? And it takes a lot of thinking and logic and thinking through it to come up with these solutions. So really, we were trying to practice the ands. So I really would probably prefer that you do it this way, but I suggest that you try both ways. I think it's kind of interesting. And if you really want to challenge yourself, flip the logic like I suggested, do less than or equal to's, start with the boomers, but the opposite end of their range and go the other direction. Let's see if you can get it to work. It's kind of a fun exercise. It's really exercise in logic, right? And this is, one of the reasons why I dig programming so much is because, like, if you're like a puzzle person, you like puzzles, programming is the ultimate kind of puzzle, and it's really healthy for your brain, by the way. Especially when you're a boomer, right? To keep your brain going and thinking about these goofy kind of things that are built on top of logic, because this kind of code would process faster than this kind of code. There's only one logical test, not two. Right? And I think that's a big takeaway here. So that's the solution to this one, folks. All right, we're going to move on to lab number 4. Let's take a look at the instructions on this. And recording is still running. Just double checking. All right, so this one is kind of sort of similar. I guess we're talking about age milestones. So it says in this lab, we're going to create functions and decision trees that inform the user of certain milestones relating to their age. All right, so the one thing that we are going to play with here, though, we are still going to do functions. We're going to use if, else if statements, elifs, whatever. We're going to use logical operators or ands, ors, or nots, perhaps. But we're also going to take a really quick look at this date time module. And I want to demonstrate how this works because they're going to basically require us to use this in the program. So first, I'm going to talk about what we're going to do in the program, and then we'll take a look at the date time thing. So, all right, so we're going to do an import of the date time library. So I'm going to show you how to do that. This import statement is incorrect, by the way. We figured this out last semester that the Python libraries changed, so I'll show you how to fix that. So we're going to create a couple different functions. One called get birth date, accepts no parameters. We get the year, month, and day from the user, and then returns a date object based on the input. So we're going to say, what month were you born? What day were you born? What year were you born? Right? Year, month, day. Right? And then we're going to convert that into a thing that is a date. Right? And the date time object, by the way, contains year, month, day, and time embedded into it. It travels as one piece of data. Right? It's a complex data object. Then we're going to get a get age function, takes one parameter, which takes the date, and then compares the parameter against today's date and converts the delta time into an integer representing the age. In other words, we're going to take the input of your, like when you were born, and tell you how old you are. Right? Seems kind of simple, but not quite so straight ahead necessarily. And then we're going to call the correct functions to get the user's age, output the following. If the user is old enough to drive, to vote, and be president, right? If the user is, now look at the language here. If the user is old enough to be president, first ask if they're a natural born citizen. How old do you have to be a president?
35?
35.
Yeah, 35 is correct, right? If the user is a natural born citizen, ask if they have been a resident for 14 years. Okay. Why is that relevant? All right. So you have to be, I don't know what the, U.S. resident for 14. Oh, I see. So if you were born here, but maybe you moved away and then you came back, you got to be here for 14 years and then you can run for president. You can't move to Canada, stay away for 30 years, then come back the next day and run for president. That no go, right? Maybe we can, you can live in Greenland, then it would be okay. That's a bad joke. I'm sorry. Kind of timely. All right. And inform the user if they are not middle-aged between 35 and 60. All right. Very uplifting, by the way. So they have a couple of examples here, right? What year were you born? What month? What date? It'll tell you how old you are. And it'll tell you can drive, you can vote, you cannot run for president, and you are not middle-aged. Okay, all true, right? Another example. 1945, okay? 77, drive, vote. Are you a natural born citizen? We get a yes or no answer. And then you cannot run for president. All right, so we have some examples here. So this is what we are going to mimic. All right, so back over to Visual Studio Code, creating a new file. All right, this for me will be mod2 lab4.py. So the first thing I'm going to do is I'm going to do a quick little example to show you how this works. And then we'll build our program. I want to show you the date time thing. So here's kind of a really weird thing about Python programming and really programming in general. All programming languages have what they call standard libraries. So in other words, when I type the print command, that one just automatically works because that's in the standard Python library. So when I write that code, Python knows what to do with it. Right? There's a lot of libraries for Pythons that are specialized to do very specific tasks. For example, there's math libraries that do really weird math calculations. There's language libraries that do really weird language things. And there's AI libraries that do really weird AI things, right? Like facial recognition. There's Python libraries for that, believe it or not. When we work with these odd libraries, we have to import them into our programs. They don't just automatically work. The standard libraries automatically work because those are standard commands. We don't want to include extra libraries that we don't need because every time we run a Python program, whatever libraries we're utilizing are pulled into the code and burden our system, perhaps unnecessarily if we're not utilizing the tools that go with it. So if I'm going to use the datetime libraries, not a standard thing we do, but if I need those, I need to import them. So the way that we do that is we write a statement like from the datetime library, import the datetime function or collection of functions, right? So this is a very specific tool within that library. By including the statement at the top, then I have access to that library, which is already on my machine, right? So fortunately it's on my machine. If not, I'd have to install it. And then I can use the datetime commands to do some stuff. So I'm gonna, this is an example, mind you. You guys don't need to code this. I'm just gonna show you really quickly. We're gonna borrow from this in our program. So, oops, and I just deleted my code on the other screen. So for example, one of the things we are going to do in our program, and we'll use this probably verbatim, is we'll write a function called get birth date. And I set up 3 variables, year, month, and day. We do a prompt, and all of the prompts are converted to integers. So the year, the month, and the day. Those are not decimal numbers. Those are whole numbers, right? 4-digit year, 2-digit month, 2-digit day, right? And then we'll return a date time object with those values. And then, all right, so let's get the other commands in here and I'll show you how those work, right? So we'll come back to the margin. And so I'll run the function. We'll return the date time object here. And then I'll run an aspect of the date time library, which is what time is it now, right? So how this works is it looks at your system clock, right, which is updated via the internet. It grabs the current date and time as a date time object, and it's storing it in another variable. Then I'm not comparing all the dates, times, year, months, and days. I'm just looking at the years. So I'm taking the now time with just the year and the one you typed in, just the year. I'm subtracting the year you put in from the year now. So if I was born in 2000, it would subtract. So I was born in 2000, it would subtract it from 2025 and tell me I'm 25 years old, and then it would print that out. Let's feel where I'm going with this, right? And I know that's a very quick explanation of how this library works, but in the interest of getting it done in time, right, we're going kind of quick on it. So here, let me show you. All right, so I'm going to put in, I'll put in my real stats, right? So there we go. Maybe the real month, maybe the real day. I'm not 61 yet, but I'm working on it. But it's an approximation, right? I'm living my 61st year, but I tell people I'm 60 years old. All right, so that's how this works. Now let's go ahead, now that we have that, those pieces in place, and I'm gonna borrow some of these pieces and kind of get rid of some of these pieces. So like, for example, I'm gonna keep the import, right? And I'm gonna change some of my verbiage. And we'll say enter the year of your birth, right? And I'm going to append that to all of the prompts. So I enter the month of your birth and the day of your birth. Okay. So this get birth date thing, that's going to flow for us. But now we're going to do the get age function. That's one that we were told to build. So let's come back here, and I'm going to define get age, parentheses, colon. This one will accept the date object that we're going to feed to it, right? So we are going to do that. So we're still going to do the now thing. So I'm going to grab this, cut, indent, and paste. I'm going to grab this calculation that we did with age. Once again, cut, indent, and paste. And then I'm going to put in a return statement here. So we're going to return the age that we're calculating to wherever it's being called from. I'm going to eliminate. Well, I'm not going to eliminate that first statement. That one we're still going to use. So we're still going to grab the date. So we're going to get the birth date, right? And then let's think about this. We're also going to, instead of hard coding the steps in the main program body, now we're going to determine the age based on that function get age, but we're sending the date into it to make it happen. So think about how this would work. I'm calling the first function that prompts the user 3 times and returns a datetime object, which stores here. Then we take that object, feed it into this function, which does the calculation and returns an age. All right. And then we can tell them, how old you are. Right. We just wait. Not what I meant to do. Again, not what I meant to do. I messed up my other screen now. Here we go. So then we're just going to output it. Same thing I basically did, but now we're doing 2 functions instead of 1. So far, this is all the code. Now we're going to get to the point where we start to write the logic that answers all those if scenarios, right? Let's do a really easy one. How old do you have to be to drive? All right. Well, if your age is greater than or equal to, at least in Wisconsin, 16, right? Then you can just output a statement like this one. You're qualified to get a driver's license. Good? Yes. All right. How old do you have to be to vote?
Yeah, 18.
Yeah, 18 is the age.
A long time ago.
Highly unfair. You can't drink at 18, right? But you can vote. There's something wrong with that equation. Alexis?
Yeah, I had a question about the get age function because instead of passing in the date, couldn't we just directly call the get birth date within the get age function?
We could. Do you guys feel like where Alexis is going with this? She's like a couple steps ahead, basically. So in other words, instead of worrying about doing it with 2 separate steps, she's saying we can use one function to call the other and do it with one function call. Yeah, you can do that. And Alexis, if you want to write it that way, I'm totally fine with it. All right, so there's the first 2 tests. All right, so now we're trying to figure out if somebody is qualified, and notice how I'm saying that is qualified to be president. And there's stipulations, right? You have to be over 35, natural born, living here for at least 14 years, and then you're qualified. But notice how the one if statement begets the other, and the other clue to this is look at how they were written here, right? First, all right, is you old enough to drive and vote? Okay, yeah, fine. Those are easy. But now we're doing the president one. First, we're asking if they're a natural born citizen. Okay, that's a yes, no, right? So we're going to learn about something else here, which is called a boolean variable, a true false, right? And then if you're a natural born citizen, have you been living here for 14 years? Another true false, right? Or yes, no. Then you let them know, right? So, and notice how one sits inside the other. So I wouldn't ask this one unless this has been confirmed and unless that has been confirmed. So in other words, the indenting of the ifs is a clue that the one if statement sits inside the other. That's how we'll structure it. Okay. So, but before I do that, I'm going to do something that's even a little bit weirder. And I'm going to introduce you to Booleans. Booleans are a special type of value in programming that basically are allowed to be either true or false. In Python, when we set up a Boolean variable, when we enter true or false into the variable, that's what we literally type. It's with a capital letter to start. And what I'm going to do is I'm going to create a thing called a flag. And a flag is a way to set a true false value so that I can flip it to true or false later based upon the logic in the if statement. So if you can follow me here on this. So when I do what I call like a Boolean flag, this is what this is. I name the variable in the form of a question because then its value makes sense. And going into it, nobody is qualified to be president. So if it is qualified, false. You're not pre-qualified, sorry, right? You got to ask the questions first, but I'm presetting it to false to set the baseline. The baseline is, I don't assume you're qualified to be president. Okay, that's why I'm setting this. So the two possible values I can put here are true or false, right? The variable is called is qualified. Okay, so now we start asking the question. First question. If their age is greater than or equal to 35. Okay. Right, so if they are, then we prompt. And we're going to say, we first set up a variable called natural born. And I apologize because I'm not fitting on screen here. So I'm going to collapse my Explorer. So I'm asking, are you a natural born citizen of the United States? And I'm asking yes or no. Okay. I'm assuming they're going to be smart enough to type lowercase y and lowercase n. But did we learn a way to convert it? We did. So you could do that conversion. I'm not really going to bother with that at this point in time. Now we're going to ask the second if statement. We're doing it inside the other if statement. When you put an if statement inside another, that's called nesting. So when I say a nested if, that means this if statement's inside the other if statement. So the next question in the series was this. If natural born equals yes, they typed a Y at the keyboard. Then I asked the next question. So I'm nesting another if. And I want you to look at, this is pretty weird, right? So I go from one if directly to another. And the next if says, oh, wait, have you been a resident of the US for at least 14 years? Yes or no? So if they say yes, then I prompt them again, looking again for a yes, no answer. And if they answer yes to this, then I take is qualified, my Boolean variable, and I flip it to true. But they had to basically clear, 3 levels of if statements. So greater than 35. Okay, well, if that's true, Are you a natural born citizen? Yes, no. If you said yes. All right. Have you been a resident for 14 years? You said yes. All right. Well, I guess you're qualified. Right. That's the layout of the land for that one. So that's how we orchestrate those ifs. Now, how do I use that boolean now to do output? All right. So now I'm going to ask the question. And watch, this is really clever. This is why I like these booleans. Because I named it as a question, if is qualified, oops. So if is qualified, not greatest English, but, and because that's already a true or false value, there's no equals, there's no greater thans, there's no ands, there's no ors. It's either true or false, right? The baseline is false. But if they cleared those three if statements, this is true. Well, then we're just going to output, you know, hey, you're qualified. Else. Okay, I'm being snarky there, but we just say that you're not qualified to be president. Right. Right. So this is the entirety of all the logic, folks. That's the whole program. So let's kind of review it really quick and then we'll test it. Right. So we have the date time stuff that we explored. We'll get the birth date. We'll check the age with that formula. We'll do it in 2 steps. You can do it in 1 if you wish. We'll display their age, see if they can drive, see if they can vote, set the flag to false. We don't assume they can be president. Check the 3 checks that we need to do. These are nested ifs. If we flip is qualified to true, they can run. If not, sorry, not happening. All right, let's run this. Control S to save. And I'll keep the bottom part of the code on the screen as much as I can. All right, enter the birth year. Let's put in something we know will work. So I'll put in my stuff. Right. Qualified for a driver's license. Yay. You're eligible to vote. You must register. Yay. Vote early and often. Are you a natural born citizen of the US? I sure am. Have you been a resident for at least 14 years? Yeah, my whole life. Thanks. You're qualified to run for US president. Last job on the planet I would want, by the way, you know, for sure. All right, let's try it again. And let's put in values that we think will break it. So I'm going to use a weird one. Let's put in, I don't know, 2009. Drive. Notice it's not telling me I can vote. And I'm not qualified to be president. All right, that's accurate, right? And you can play with all the values and try all the if statements. And if you were to do your due diligence, and I would suggest you do this when you run a program, is let's put in a value that we know will work. So 1950, whatever. Are you a natural born citizen? Well, maybe I should say no. Okay, you're not qualified. Let's run it again. You know, and the point of this is to hit all the scenarios, right? Let's say yes to this one, and then say no to that one. Okay, right. So all of it is working. And then once again, let's run it again with values we know will work. Yes. Yes. All right. So I've tested all the pathways in the program. And so normally, you know, like when you guys are going to do screenshots for this, right? I don't need you to screenshot every possible output scenario, but I would like you to test all the output scenarios to make sure that they're all hitting, because maybe you didn't write it correctly and maybe something is not actually working. Right. So that I would caution you, especially when you're writing like a piece of software that you're, you know, expecting to work correctly, and it has all these possibilities in it, you need to test all the possibilities to make sure that every branch of every if statement is being considered. If you find a more efficient way to write this, I'm all eyes and ears. I'd love to see it, right? All right, we're gonna wrap. This video is gonna end here. So I'm gonna stop this video right now.